Yes. Okay. So sorry again for the delay. So my name is Albert Cohen from Google. I will be chairing the first session on compilers. So we have a couple of talks on like graph analytics, graph algorithms, a couple of talks on polyhedral compilation, and then two more talks on program analysis. So the first presentation will be given by Anchu Rajendran from IIT Madras, and I will let you show the video, and then we will have a 5 minutes question and answer session.
Thank you. Hello and welcome everyone. Here I will be presenting our work on DisGCo, which is a compiler for distributed graph analytics. So we know that graph programs are used by a variety of applications in day-to-day life, processing real-world graphs, which are really huge in size, in order of trillions of vertices and edges. And performance of these applications have turned really crucial. So various libraries, domain-specific languages, and frameworks are proposed in the literature. Among them, if you consider domain-specific languages, they provide a higher level of abstraction, thereby easing programmability and contributing to some intuitiveness for programming. And Greenmall is one such domain-specific language targeting various backends. And the current backends are for OpenMP, CUDA, and Pragal. And Pragal is for distributed systems. So if you consider distributed systems offer huge storage as well as proper processing capabilities, and they form an ideal platform for graph processing. However, usage of this intuitive graph DSLs in the domain of distributed systems is still in its nascent stage. So what we have developed is, we have developed a compiler called DisGCo, which can translate any general program written in the intuitive DSL Greenmall to its corresponding program in MPI. We know that MPI is known for its portability as well as performance. Now, let me cover some background information that are needed for understanding the work, starting with Greenmall. So Greenmall, as I said, is a domain-specific language and follows a shared memory-like programming style. Here, the parallelism is confined to for each loop. The iterations of the for each loop are expected to be executed in parallel. Now let's see a sample example in Greenmall. So this says a procedure, triangle counting, which counts the number of triangles in an undirected graph T in a variable T and returns the variable. So there is a triply nested loop, as you can see. The first loop iterates over the nodes of the graph, second loop iterates over the neighbors of the node, and third loop also iterates over the neighbors of the nodes. So if these two nodes are connected, they form a triangle, and we increment the count by 1. So with these loops, you can see a Boolean condition encoded. In Greenmall, it says that if a Boolean condition is encoded, an iteration of a particular loop will be executed only if it satisfies the condition. So in this case, this Boolean condition is used to ensure there is some kind of ordering and no triangles are counted more than once. Now let me cover some background information on MPI as well. So based on the previous slide, it's well clear that it's pretty intuitive to write programs in Greenmall. So now let me cover some information on MPI as well. MPI traditionally uses single program multiple data style of parallelism, where the same program will be executed by multiple processes in parallel. In MPI, the processes are identified by an unique identifier called rank. So figure shows the case where there are two processes, one with rank 0 and other with rank 1. So in the traditional system, if the processes want to communicate data, they communicate using sending and receiving messages. So even if you want to read or write data, both the parties of communication need to be present in the scene. However, in this case, as the same program is executed by multiple processes, if you want a particular program to execute a particular process to execute particular piece of code, you'll have to write something like this. You will have to wrap the piece of code in if statement saying if your ID is so and so, do this particular piece of code. However, with MPI2, they introduced a new programming model similar to shared memory like programming style called MPI RMA, where if a process wants to read or write the data, then what it will have to. So the other party, in this case, if you are using MPA RMA to program, only the reader or the writer needs to be present in the scene. And this is similar to shared memory programming. So when we started designing the backend of DisGCo, the first question was whether it should be MPA point-to-point or MPA RMA. So studying the literature, we found some supporting works which shows that point-to-point programs are better than RMA. So RMA programs are better than point-to-point programs for graph algorithms. So we have designed DisGCo to admit any arbitrary green code, and DisGCo generates the equivalent MPA RMA code for it. We also want to highlight that the compilation techniques we use in DisGCo can be used for compiling any similar DSL which follows a shared memory like programming style, for example, DH-Falcon or Graphite. Now, let me give a brief summary of the compilation techniques used in DisGCo. I'll explain the challenges and tell how we have solved these challenges. So as I told, the parallelism specification itself is different for DisGCo, different for Greenmal and MPI. So in MPI, it's single program multiple data kind of parallelism, whereas in Greenmal, it's confined to for each loop. Moreover, if you see Greenmal programs, they are a combination of sequential and parallel code parts. There will be for each loops preceded or succeeded by sequential code parts. So we need a good mapping between these for translation. Moreover, translation of each Greenmal construct depends whether they are present inside a sequential region or a parallel region. So we have devised the translation logic, and we have given the distributed implementation of all Greenmal constructs. We have also devised a few optimization for efficiency. One is the communication aggregation optimization, and other is the common sub-expression elimination. So I would like to add some points to the communication aggregation optimization. Here, in this optimization, we reduce the number of communications in a set of programs, a set of Greenmal programs with some commonly occurring communication patterns. I would also like to highlight that, to the best of our knowledge, this set of programs is a superset of the programs that are compilable by other graph DSL compilers targeting distributed backends like DH Falcon or the Pragal backend of Greenmal. So for those programs that could be compiled by those compilers, we can generate optimized programs. Another important requirement for performance the execution of graph program is load balancing. So there are many prior works in this area. How we have solved this challenge is that we have added support in DisGCo for the user to specify any arbitrary vertex distribution as input to the DisGCo, so that he can ensure that the input is well load balanced and get a performance out of it. Not only good programs and good load balancing are required for performance, we also require efficient graph representation for performance, good data structures so that accesses happen in a space and a time efficient way. So we have designed a good representation called distributed compressed sparse through. Now let me discuss the evaluations we have done on DisGCo. We have conducted 4 main evaluations. First, we have studied the scalability of the generated codes. We have compared DisGCo programs against the state-of-the-art DH Falcon generated programs. DH Falcon generates MPI point-to-point codes from the codes written in their DSL. We have also studied the performance of DisGCo for various distributions. We have also studied the effectiveness of optimizations we have devised. So these evaluations are performed on an IBM cluster with 16 nodes, and each node has up to 16 cores, and the nodes are connected using InfiniBand interconnect, and the network is RDMA enabled. So all through this evaluation slide, an evaluation configuration mentioned as N cross C indicates that the evaluation is done on N nodes with C cores each. Now, these are the inputs and benchmarks which are used for evaluation. So we have used five different inputs where the number of vertices ranges from 0.4 to 30 million and number of edges range from 3 million to 300 million. And so these are the five benchmarks used for evaluation. This shows the scalability of the DisGCo generated programs in a purely distributed setup. So if you see the x-axis, you can see that the number of nodes varies from 1 to 16, whereas the number of cores remains to be 1, which shows that it is a purely distributed setup. And if you see the y-axis, this shows the speed up over the running times of sequential configuration over these configurations. Yeah, and this shows that the programs are scalable. However, for some inputs, we can see that after some point, the scalability decreases. So this is the point where the performance due to parallelism are overshadowed by the communication overheads involved. So these graphs shows the comparison against the state of the art work DH Falcon. DH Falcon could compile only 3 benchmarks, and for those benchmarks it could compile, and for those configurations it could run. Our programs were performing better than DH Falcons. So now going into the conclusion, so we have designed and implemented a new compiler called DisGCo, which can handle all syntactic capabilities of a practical graph DSL called Greenwald and generate MPA RMA programs for all Greenwald programs. So, however, for those compilers which are existing that could target distributed systems like the Pragal backend of Greenwald or DH Falcon, for those programs that could be handled by them, we are able to generate optimized MPA RMA programs. There are many interesting directions in which DisGCo can be extended, such as we can optimize the library implementations we have done, and we could also implement new optimizations for reducing synchronization. So all these details are covered in detail in paper. I would highly recommend to read the paper to get a clear understanding on this. And DisGCo is available for use in the link that is mentioned below. And thank you. We'll go into questions if any.
Thank you very much for the great presentation. Again, this is an online event, so the Q&A session is really essential. That's the one and only occasion to, not the only one, but the main occasion to discuss with the authors. So please ask questions on the chat. And if needed, I can also, maybe the panelists can also use the mic, but please ask the question on the chat first. So in the meantime, I will ask a question. So you mentioned that your approach could be more widely applicable, like starting from a shared memory DSL, like Graphite or DH Falcon. Can you explain a bit more in more detail what kind of benefits and how you would envision leveraging your approach in these settings?
Yeah, I can. Thanks for the question, Albert, and thank you everyone for attending the talk. So about the question, the technique which we used here is MPA RMA. So MPA RMA is the communication is more like an one-sided approach, and whereas point-to-point is more towards two-sided. So most of the compilers existing today uses point-to-point, and it's kind of restrictive because as both senders and receivers are in the picture, for any read or write, both the parties need to be present at the scene. However, RMA can be used if hardware has proper support. RMA can be used in a similar way we use the shared memory programs. Like for a single read, we can in RMA how it works is that we can expose the data to all to the group where communication has to take place, and the processors can, with one-sided access, they can easily access the data. So this has an equivalent model to shared memory programming, and yeah, that's a vision. Yeah, RMA better suits such programming models.
Okay, one last question because we are short on time. So Sanjay Rajapati from Colorado State is asking, are there situations in your DSL where MPI collective communications can be profitably used?
Yes, Greenwald do support reductions, something like mean reductions, additions everywhere, where MP collectives like for reducing collectives can be used, and as well as, however, I have not used scatter or gather or something like that, but we can explore those things. But reductions are used in a very nice way so that we could reduce the communications to log and from sequentially reducing. Yeah.
Thank
That's
you, very
used.
clear. So let's thank Chandu again. And we'll turn to the second presentation. So again about graphs. This time, Yu Zhang from Huazhong University of Science and Technology in China will give the talk. And this is joint work with colleagues from National University of Singapore. Waiting for the video to show. Yeah.
In this talk, I will present a system called AsynGraph. It is a system to fully exploit the high parallelism of GPUs for faster convergence speed of iterative graph processing. To begin with, I will present the background and the challenges of iterative graph processing on GPU. Graphs widely exist in real-world applications, hence many iterative algorithms are designed to handle these graphs iteratively until the user-given condition is met. In order to speed up these time-consuming iterative graph algorithms, many GPU-based systems are designed, such as Kusha, Groot, Tiger, Digraph, SIMDX. These solutions support efficient iterative graph processing on GPUs through ensuring collapsed memory access, better data locality, balanced load, fewer updates, less communication cost, and so on. However, existing GPU-based solutions suffer from low utilization ratio of the GPU because of slow state propagation. Most vertices on graph paths are processed by different GPU threads concurrently. These threads may use their neighbors' still states to update their own states within each round before the updating of their neighbors in the same round. It eventually induces poor performance for iterative graph processing on GPUs. For example, with existing GPU-based solutions, the path V1 to V17 of this figure may be put into several partitions, and each partition is handled on one SM. Vertex states in a partition, for example, partition 0, need to traverse several SMs to reach the vertices of the other partitions. In detail, after the processing of partition 0, the still state from partition 0 can reach the vertices of the partition 1 and partition 2. Consequently, many partitions' vertices may have been updated based on the still vertex states in the partition 0 for several rounds before receiving the most recent vertex states from partition 0 and need to be reprocessed. In addition, when a partition is assigned to SM by existing solution, its each path vertices are also usually concurrently processed by its different threads. As a result, lots of cross-core propagation are generated, which lead to slower convergence speed because of frequent reprocessing of many vertices. The above slow state propagation not only incurs many unnecessary updates, but also makes many vertices be inactive during several rounds. In practice, due to the power law property of natural graph, a small set of high-degree vertices are connected with much more vertices than the others. And thus, the paths between a few vertices play a more important role on vertex state propagation. This fact allows us to boost iterative graph processing's convergence speed on GPUs through boosting state propagations on a small set of paths. Based on this fact, an efficient structure-aware asynchronous execution approach is proposed in this article to fully exploit the high parallelism of GPU for faster convergence speed of iterative graph processing. Take this figure as an example. We first evaluate a vertex VH's importance on state propagation. The vertex VH is identified as a hub vertex when its importance value is higher than a threshold T. In the pre-processing stage, for fast state propagations on GPU, we first extract a set of graph paths between the hub vertices from the graph to construct a small graph sketch. Take this figure as an example. The identified hub paths, for example, V3 to V7 and V7 to V16, constitute the graph sketch and are put together into several hub chunks, for example, PS, while the remaining parts of the graph are put into many code chunks, for example, P1, P2, and P3. By such means, it enables efficient asynchronous intra-path state propagations along graph paths. To efficiently store the graph, 4 arrays are used to store the set of disjoint paths on GPU. This figure shows how to store the chunk P2 of the graph example on GPU. It uses EIDX and S'(VAL) to store the indexes and the states of the vertices, respectively. The values of the edges on each path are stored in EVAL accordingly. For quick access of each vertex state, a separate array SVAL is also maintained. The information of the path to be processed by each GPU thread is stored in its local table, GT. The right picture illustrates the way to store the arrays EIDX and S'(VAL). In this way, when loading a contiguous range of EIDX, S'(VAL) and EVAL into an SM for a warp, each GPU thread of this warp has the related data of its own path to handle. By such means, it enables collect access for parallel processing of graph paths over these GPU threads. Then at execution time, the paths in the graph sketch are handled multiple times within each round of graph processing, while the code paths are only handled once. By such means, the graph sketch can serve as a fast bridge for most state propagations, and the higher parallelism of GPU can be utilized to accelerate these propagations. However, the above processing methods may suffer from load imbalance because processing behavior of hub paths and code paths is different. To efficiently get our goal, as depicted in this figure, long-running persistent GPU threads are generated over the SMs to repeatedly load chunks from global circular hot or cold queue and asynchronously handle the related active chunks until the queue is empty. For a balanced load between SMs, the chunks assigned to warps of overloaded SMs can be stolen by warps of the free SMS. In addition, asynchronous intra-path propagations along each path may be inefficiently conducted when these path vertices are only asynchronously updated in one direction. For efficient asynchronous intra-path propagation along each path, a forward-backward path processing way is also implemented, aiming to further boost propagations along paths and also ensure smaller data access costs. According to the storing order of each path vertices, these vertices are first handled in a forward direction, then in a backward direction until convergence. The experiments are performed on 4 PCS with 4 GPUs. The details of the data sets are shown in this table. Our experiments show that AsynGraph performs much better than existing solutions. As shown in this figure, Gunrock, Groot, and Tiger need more graph processing time than AsynGraph. because they need to deal with more updates and also require a higher cost to transfer unnecessary data into SMS. Besides, AsynGraph outperforms DisGraph thanks to more efficient utilization of high parallelism of GPU. Then we evaluate the average GPU utilization ratio of PageRank and TripSP over different systems. As observed in this figure, AsynGraph has the highest ratio due to faster propagation of vertex new state and smaller data access cost, where handling the graph along paths in a FB way for better temporal locality. In summary, we propose an effective structure where asynchronous execution approach to fully exploit the high parallelism of GPUs for faster convergence speed of iterative graph processing. In future, we will research how to extend AsynGraph to heterogeneous platforms for large-scale graph processing, and also extend AsynGraph to efficiently support involving graph processing over GPUs using an efficient incremental way. We will also research new software or hardware cooperative approach for high-performance graph processing, including involving graph processing and streaming graph processing. Thanks for watching.
Thank you very much for a very clear talk. So once again, please ask questions on the chat. I have a first question myself. So it was not very clear to me how you actually copy the data, the graph onto the GPU and choose the data structure at that point. So what overheads do you have when doing that? And yeah, basically how you maybe amortize this overhead.
Sorry, can you text your answer on the book?
Okay, yeah, I can do that.
Sorry.
Oh, sorry, that's I put it on the chat, which is stupid. Sorry about that. I'm not sure I can actually. I think by default, so let me repeat slowly. So the question is, how do you account for data transfer overheads, like from CPU to GPU? Did you count this? And how did you amortize the cost of selecting a data structure that's appropriate for the asynchronous execution? I'm not sure I understood in the experimental evaluation how this was accounted for.
Can you repeat your question? Sorry, the student of Professor Zhang, so some questions I can't understand. Sorry.
Yeah, maybe the sound is not so good. I just don't see how I can actually type a question in the Q&A on my side. Some Zoom mysteries. Okay, thanks, Vincent.
Oh, okay. I can see your questions. The chunk are dispatched from the CPU to GPU, and we also create multiple streams to overlap the kernel execution overhead and the memory transfer overhead.
Okay, so this was actually taken into account in your evaluation. You counted these costs in the evaluation.
Our data structure is described as I mentioned in the slides, and do you mean the data structure like CSR or something else?
Ram, did you hear the answer to your question? The question as an answer to your question? Yeah, I think that's the correct answer. But... Okay, so I think we are running out of time. I don't see. Oh, okay. So Ram was okay. Thank you, Ram. No, yeah. I was focusing on the data transfers, Ram. So I think the answer was fine. So we are running out of time. There seems to be an issue with Q&A because I don't know if other panelists can ask questions on the Q&A, but at least on my side, it seems to be blocked. I can only ask questions live. Okay, so we'll thank you, Zhang again, and we'll continue with the next presentation. Thanks for the presentation. So the next talk will be PolyDL. This is joint work from Intel Labs in India and IIT Hyderabad. And the presentation will be given by Sanket Tavarageri from Intel.
Hello, I'm going to present our paper PolyDL, Polyhedral Optimizations for Creation of High-Performance DL Primitives. This is a work we performed at Intel Labs along with our colleagues at IIT Hyderabad in India. Deep learning and in general artificial intelligence is becoming ubiquitous. DL inference tasks are predominantly run on CPUs. A recent McKinsey study indicated that 75% of the DL tasks are run on CPUs. Therefore, optimizing deep learning workloads, especially for inference tasks on CPUs, is an important problem. And achieving high performance on CPUs is a challenging task because of the architectural complexities of the CPUs. We have multi-level cache hierarchy to be able to reduce the latency of data access on CPUs. And we have wide SIMD units on CPUs for which the workload has to be optimized for. Currently, the state of practice is to use high-performance libraries such as Intel 1DNN along with the deep learning framework such as TensorFlow and PyTorch to optimize DL workloads. However, development of a library could be labor intensive, and with the advent of newer DL primitives, it may not be scalable. In this work, we strive to achieve performance and productivity at the same time. The overall system architecture of our system PolyDL is depicted in the picture. The input to the system is a loop nest. The loop nest could be that of a naive implementation of convolution or a gem, and optionally a microkernel. In this work, we emphasize on two aspects of program optimization, namely outer loop tuning for efficient use of cache hierarchy so that the data reuse is optimally done, and optimization of inner loops for vectorization. For optimization of inner loops, we rely on microkernels. Microkernels are hand-coded implementations of the inner loops. Prior work has shown that many of the popular DL primitives, including convolutions, gems, and LSTMs, can be formulated in terms of matrix multiplications. Therefore, in this work, we use high-performance implementation of gems, matrix multiplications, and focus on optimizing the outer loops. Together, we show that we are able to achieve high performance for convolutions and gems. Then the system, PolyDL system, will generate various code versions that are tiled and whose loops are permuted. The loop variant code generator will try out different tile sizes as well as different loop orders. Our contribution is development of novel algorithms to choose among different code versions at compile time which ones will perform the best. And the PolyDL system will pick top k versions. K could be 1, k could be 5%, it is parametric. And those top k versions could be run on the target architecture, and absolute best versions could be selected. The selection of best code versions is done in two phases. First, for each code version, we compute working set sizes, and then from compiler derived features, we'll perform ranking among those code versions to select top k versions. We enumerate the data dependencies in the program. There are 4 kinds of data dependencies in a given program, namely read after write, write after read, write after write, and read after read. We enumerate all the 4 kinds of data dependencies. The key insight of our work is that each data dependency is also an instance of data use. Therefore, when we compute working set sizes for data dependencies, we will be figuring out which code versions will utilize the data uses out of the caches that are closer to the processor. That provides us the basis for ranking different code versions later on. And for each data dependence, we will compute its working set size, which is defined as the number of data elements accessed between the source and target iteration of the data dependence. The other input to the system is the cache sizes of the CPU, namely L1, L2, L3 cache sizes. And for each data dependence, we'll figure out if that data dependence and hence the data reuse can be exploited out of L1 cache or L2 cache or L3 cache. Accordingly, we'll update the working set sizes for L1, L2, and L3 cache memories. The compiler for each code version will generate these statistics, working set sizes for each of the caches. And we use a 4-layer feed-forward neural network to predict between the 2 code versions which one will perform better. We first train the neural network using performance data, and then for inferencing at production time, we will simply use the model that is already built to predict which among the N code versions will perform the best. For this purpose, we will use a tournament-based ranking system where each code version is pitted against every other, and the code version that has accumulated the most number of wins would be considered the overall winner, and the one with the next highest number of wins would be considered the next winner, and so forth. Using this methodology, we performed extensive experiments on convolutions and GEMS, matrix multiplications. Convolutions appear in CNN models for image recognition, and GEMS are widely recognized to be at the heart of deep learning for MLPs and feed-forward neural networks. Here, the performance of our system PolyDL achieved for convolutions of ResNet 50 layers are shown. There are 19 distinct convolution layers in ResNet 50 CNN model. And we run the experiments on Cascade Lake servers. We compare the performance of our system PolyDL with that of Intel 1DNN library, which is a hand expert coded library. We also compare the performance of PolyDL with AutoTVM, an auto-tuning system. We note that the performance of PolyDL is very similar to that of 1DNN library and is higher than AutoTVM. We also note that Autotv takes much longer to derive high performance implementations, to identify high performance implementations. On average, we found that PolyDL could be 20x faster compared to AutoTVM in terms of its ability to arrive at high performance implementations in terms of time. In summary, in this work, we developed polyhedral compilation based techniques to perform loop optimization. We took a two-pronged approach where we use the novel polyhedral compilation techniques to optimize the outer loops, and we used microkernels for inner loops. Because most DL primitives can be formulated in terms of microkernels, the number of microkernels that we expect need to be coded by expert programmers is very few. In fact, currently a single microkernel, namely GEM, would suffice in being able to support multiple popular DL primitives. The compiler algorithms that we have developed and presented in the paper will determine the loop order, the correct loop order and tile sizes for the loop nest. We expect that this will ease the development of high performance libraries for deep learning workloads. Thank you.
Thank you very much, Sanket, for a very clear talk. So once again, please ask questions on the Q&A. I see one question already. So Alex Zinenko from Google is asking, there are some kernels where PolyDL looks significantly faster than 1DNN and some where it's not. Is there a good explanation and why?
Yeah, sure. Thanks for the question. 1DNN development of 1DNN library is more or less a manual process. So there is a huge search space, and the programmers will tune the primitives to a certain extent, and some of the opportunities might have been missed. So that explains where PolyDL performs better than 1DNN, and conversely to the PolyDL system chooses among the presented versions which one will perform the best. So in cases where PolyDL is slightly slower than 1DNN could be explained by the fact that some of the schedules might not have been input to the PolyDL system in the first place. So these could be taken care of by having a more extensive search for schedules and presenting the schedules to the PolyDL system.
Thank you. That's legitimate. Second question from Professor Ramanujan. Nice work. Please provide some idea on how you compute working set sizes in the case of parametric or symbolic loops.
Yeah, in this instance, as far as this work was concerned, the runtime parameters, the problem sizes of the convolutions and gems were known. So this is more or less envisioned to be a custom runtime compiler, JIT compiler, at which point the sizes will be known. So we can think of ways to make some of the underlying algorithms work for parametric tile sizes, also parametric problem sizes as well. So, but that was not addressed as part of this work, but a great question and possibly a good future direction.
Yes. And last question from Sanjay Chopadier. The advantage of DSLs is to enable programmers to write new programs. That's one of the strong advantages. Did you experiment with new programs or like new layers or only try to replicate existing ones?
Yes. So we presented some of the results, especially with regards to fusion. We presented some techniques for fusing different operators as well, which I didn't cover in the presentation. However, as part of that experimental evaluation, we evaluated with newer operators which are not supported in the standard 1DNN library, such as ReLU 6. Which caps the value of the output of the ReLU operator to be 6, for example. So these innovative operators have been used in some research neural network architectures, but are not supported as part of 1DNN. And that shows that some automatic compilation techniques such as PolyDL will be crucial to achieving high performance for newer operators such as those.
Okay, thank you very much. So if you have more questions, please use the Q&A, and Sanket can answer offline. Thanks again. So we move on to the fourth presentation. This time it's a little bit embarrassing because I'm also a co-author. But so please ask questions, so that would be easier. So this is joint work between the IISc in Bangalore and Google, and the presentation will be given by Aravind Acharya.
Hello everyone, welcome to my talk on effective loop fusion in polyhedral compilation using fusion conflict graphs. The outline of the talk is as follows. First, we'll see an introduction to polyhedral auto-transformation frameworks. Then we'll see what fusion conflict graphs are and how we use them to model parallelism-preserving loop fusion heuristics in the polyhedral auto-transformation framework. And we'll finally conclude with some experimental results. Affine transformations include loop permutations, loop scaling, loop shifting, loop skewing, loop fusion, distribution, loop reversals, and complex combination of these. In general, an affine transformation can be represented using a transformation matrix. The elements of this matrix are called transformation coefficients. Polyhedral auto-transformation frameworks find these transformation coefficients for all statements in the program. Once these transformation coefficients are found, code generators like Klug, Omega Plus, ISL are readily available to generate code for the transformed loop nests. There are many polyhedral auto-transformation frameworks proposed in literature. With these transformation frameworks use ILP or LP formulations to obtain the transformation coefficients. The objective functions of these ILP formulations either encode to minimize latency or synchronization, or maximize locality or parallelism, and complex combinations of these. In this work, we'll look at Pluto's auto-transformation algorithm as it is used in some form or the other in all the other auto-transformation frameworks. Consider the example program shown here. It has two statements, each of them in a one-dimensional loop nest. Both the loops are parallel. However, when we transform the code using Pluto, it gives us a fused loop nest where the fused loop nest is sequential. This is because Pluto's cost function favors fusion or locality even if it comes at the expense of loss of parallelism. In this work, we'll see how to incorporate parallelism-preserving loop fusion heuristics in the Pluto LPDFP framework without actually introducing more number of ILP, without actually introducing a significant compile time overhead. The Pluto LPDFP framework, which we had proposed in PLDI 2018, decoupled the auto-transformation framework into three phases or three components. The first component was fusion and permutation component, followed by loop scaling and shifting component, and finally a loop skewing component. This decoupled modeling allows us to model different loop fusion heuristics alongside other loop transformations. We assumed that the fusion and permutation component was a black box in our PLDI work, and in this paper, we actually describe the details of this black box. The output of fusion and permutation stage of the Pluto LPDFP framework is a valid permutation. The formal definition of valid permutations is available in the paper. Consider the example code shown here. It is from the Gemware kernel from Polybench. It has two statements, each in a 2D loop nest. The two statements cannot be fused completely because it violates the raw dependence between the statement S1 and the statement S2 due to the transposed axis arising due to the transposed axis of the array A. Therefore, the permutation shown here, which corresponds to the identity transformation, is invalid. However, if we interchange the two statements, two loops of the statement S2, then we get the transformation where the second statement has JI loop order, and one should be able to fuse the two loop nests completely. However, you can also interchange the loops for the statement S1, giving the transformation shown here, which also has outer parallelism. Therefore, there are many possible valid permutations, and we would want a model to choose among one of these. In general, valid permutations represent the permutation component of the final transformation. They also enable us to model loop fusion alongside other loop transformations. So the key to finding valid permutations is a fusion conflict graph. The vertices of this graph correspond to dimensions of the statements, and edges represent a pair of dimensions that cannot be fused and permuted to the outermost level. This is the fusion conflict graph for the FTTD2D benchmark from Polybench. It has 4 statements and a 3-dimensional loop nest. So this is the graph that we get. And what we show in the paper is that convex independent sets of the fusion conflict graph represent valid permutations. So the formal definition of convex independent sets is available in the paper. We'll see an example. The independent set S1T, S2T, and S4T is a non-convex independent set because there is a path in the data dependence graph, namely S1, S4, S3, and S4. That is a path from S1 to S4 which goes via S3. But there is no vertex corresponding to the statement S3 in the convex independent set. Therefore, this is a non-convex independent set, whereas an independent set consisting of S1T, S2T, S3T, and S4T is a convex independent set. We find these convex independent sets using a custom coloring algorithm. We'll first see how to construct the FCG. Coming back to the example of gemware, we had 2 statements and each in a 2-dimensional loop nest. So there are 4 statements in the 4 vertices in the fusion conflict graph. We incrementally add edges in the fusion conflict graph using LP formulations. So first we add intra-statement permute preventing edges. In this case, all the dimensions were permutable, and therefore we don't have to add any intra-statement. We don't have any intra-statement edges. They usually appear as self loops on the vertices of the fusion conflict graph. Then we add inter-statement fusion and permute preventing edges. So as these edges now in the gemware case prevent the identity transformation. And we also add parallelism preventing edges only when we are aiming at parallelism preserving loop fusion heuristics. So these are shown in blue in the dotted blue lines throughout this presentation. So these edges enable us to encode parallelism preserving loop fusion heuristics. And finally, we also add edges between vertices corresponding to the same statement, dimensions of the same statements. As you can see, there are a large number of LP formulations that we use, and in order to reduce them, we use a clustering heuristic based on the SCCs in the data dependence graph. In this case, there are 2 SCCs and 2 statements, so the clustering will not improve the LP reduce the number of LP formulations any further. So every statement in the clustered FCG, in the clustered fusion conflict graph, is assumed to have the same transformation at a given level. Once we construct the fusion conflict graph, we start coloring the fusion conflict graph to find convex independent sets. So we assume that the colors are ordered, and an ordering of the colors actually defines the final permutation. So when we start coloring for the fusion conflict graph of the gemware case, we have 2 vertices that we can choose to color from. If we color the vertex S1I, then we cannot proceed further. But if we color S1J, it will also enable us to color S2I. Therefore, the greedy heuristic that we choose is to maximally choose a vertex that allows us to maximally color the fusion conflict graph. That is, it tries to maximize the number of vertices that can be colored. So here we choose the vertex J of statement S1 at the outermost level, which corresponds to an interchange for the statement S1, and then we proceed to coloring the vertex S1I with the second color, and now we cannot proceed further again. So in this case, when coloring can fail due to two cases, either due to a fusion preventing edge or due to a permute preventing edge. When it fails due to a fusion preventing edge, we remove the dependencies that are satisfied at the outer levels and rebuild the FCG. And if it fails due to a parallelism preventing edge or a fusion preventing edge, then we distribute the loop nests. In this case, it was due to a parallelism preventing edge, so we distribute the loop nests. However, this distribution resulted in loss of register reuse. Note that there was already an outer parallel loop. Therefore, we introduce a hybrid fusion strategy which ignores the parallelism preventing edges while coloring, and then proceeds with coloring the fusion conflict graph as if the parallelism preserving edges were not present, only when the outer parallel loop was already found for a given SEC. After we color the fusion conflict graph, we obtain the valid permutation shown here, where the first statement has a loop interchange. This was the desired transformation that we wanted. So the Pluto LPDFP toolchain is as follows. From the polyhedral dependencies, we perform a stencil check. I did not discuss the details of this check in this talk. The details are available in the paper. Once we classify an SCC as a stencil, we employ a max fusion heuristic for these SCCs after separating them from the rest of the auto transformation from the rest of the program. We actually construct the fusion conflict graph and color the vertices to find convex independent sets. Then we perform loop scaling and loop shifting transformations. Then we perform loop skewing if and only if it is profitable. We also improve the intratile optimization heuristics and unroll jam optimizations in Pluto. So these two improves the performance of the baseline as well. So the benchmarks that we used for evaluation are the RHS routine of BT, LU, and SP benchmarks from the NAS parallel benchmark suite and Polybench 4.1. The former NAS benchmarks were used for compile time analysis, while Polybench was used for measurement of performance of auto-transformed codes. The baseline auto-transformation frameworks that we used were the implementation of POC by Kong et al. PLDI 2019 and the version of Pluto. So our experiments were conducted on a 16-core Intel Skylake machine. So in case of Polybench benchmarks, especially the stencils, we observed a performance improvement of 1.9x over diamond tiled stencils. This was because the transformation found by Pluto LPDFP enabled better L1 cache reuse. In case of linear algebra benchmarks, the hybrid fuse variant had a performance improvement of 1.23x over Pluto. Note that Pluto's performance by itself had improved by over a factor of 2x. So the 1.3x improvement was over the improved version of Pluto. In terms of auto transformation time, Pluto LPDFP was faster than Pluto by an order of magnitude over 200x, and POC did not terminate on these benchmarks for over 10 hours. Moreover, the incorporation of parallelism preserving fusion heuristics, that is the hybrid fuse variant shown in this table, had a small compile time overhead of 5.2% as compared to the max fuse, which did not have parallelism preserving loop fusion heuristics. So in general, parallelism preserving fusion heuristics were incorporated at a very small cost. The whole tool is available as a part of Pluto. To conclude, we proposed a data structure called fusion conflict graph to efficiently model loop fusion. We used clustering heuristics and incorporated parallelism preserving loop fusion heuristics to work in tandem with other affine loop transformations, and these did not have any significant compile time overheads. We also characterized stencils based on the properties like the presence of concurrent start, the absence of communication-free loop nests, and we employed a different fusion strategy for such program segments. We observed performance improvements of 1.8x over POC and 7% over Pluto without sacrificing the compile time gains of Pluto LPDFP over Pluto. I would like to thank Martin Kong for sharing his implementation of the PLDI paper, Indria and Cefipra for funding the collaboration between ENS and IISc, and NVIDIA for supporting my registration to HighPeak 2021. Thank you.
Thank you, Aravind. A little bit behind, the presentation was a bit long. Alex Zidenko is asking again, it's unclear if shifting is also considered in the fusion permutations or separately. And sometimes one can shift to resolve a fusion conflict. So how do you model this? Is this model?
Shifting can actually result in, especially it can, shifting can lead to loss of parallelism, as in you can have conflicting shifts which lead to loss of parallelism. But if you are just considering permutations and fusion, it does not, because you can always a shift introduces a delay, and you can always delay the you can always accumulate shifts and have a fused loop nest. So you won't have conflicting shifts in terms of just permutations and tiling, but you will have conflicting shifts for for parallelism preserving fusion heuristics. And we actually distribute the loop nests when we find these conflicting shifts by a traversal over the fusion conflict graph. While constructing it, we actually add a few more edges, and the details are present in the paper.
Thank you. Second and last question, Vincent Lechner is saying, nice work, and is asking, there can be many versions of a fused or unfused loop nests, even for small programs. Do you run the LP solver scheduler on each of them to find the best version in the second step, or do you determine which one will perform best?
So we construct the fusion conflict graph only once. So that means that all the fusion combinations would already be encoded. So our coloring heuristic will actually derive which one of these fusion or fusion permutation combinations are chosen. So so the coloring heuristic will determine max fuse or permutations, whichever you are. Parallelism preserving heuristic, whichever you want, you can choose it, and that would give you pick one of the variants. So it's not that we enumerate all of it.
Okay, thank you, Aravind. So we are going to switch to the next presentation. So this is about data race checking, static data race checking. The presentation will be given by Utpal Boa from IIT Hyderabad, and this is joint work with colleagues from IIT Hyderabad and ISC. No, sorry, and Colorado State. I'm getting confused. This one is with IISc, Colorado State. Yeah. We have a lot of presentations from IIT Hyderabad today. So let's tune in for the presentation.
Hello everyone, I am Utpal Bora. Today I am going to present our work, LLOB, a fast static data race checker for OpenMP programs. This work is in collaboration with Shantanu Das, Pankaj Kukreja, Dr. Saurabh Joshi, Dr. Ramakrishna Upadrasta from IIT Hyderabad, and Dr. Sanjay Rajopadhyay from Colorado State University, United States. OpenMP is a parallel processing framework which enables shared memory parallel programming in a multi-threaded system. Even though parallel programming is easier with OpenMP, however, it suffers multiple data race conditions. One such category is because of missing data sharing clauses. As shown in listing 1, variables in OpenMP are marked by data sharing clauses as private, shared, or reduction variables. Since the variable sum is not marked as private or reduction, this variable will be shared among all the threads in the program. However, there are no locks protecting the memory accesses at line number 6. Hence, two simultaneous memory writes will result in data races. There can be races in OpenMP programs because of incorrect parallelization of the programs. As shown in listing 2, there can be data dependencies in a loop nest. Here, the dependencies is from B of ij to Bij-1, which is from iteration ij to iteration ij-1. That means that dependency is carried by the inner dimension. At the same time, the user has marked the inner dimension as parallel. This will result in data races. There can be data races because of singleton constructs as well, which is similar to loop carry dependencies, except that such issues can happen within a single hardware thread as well, because modern processor has vector processing units which will suffer from the same problems. Synchronization issues is a common problem in any parallel programming framework. Synchronization issues may result in data races as well as deadlocks. For example, as shown in listing 4, because of the no-if clause, there will not be a barrier after line number 6. Hence, two threads might execute statement at line number 6 and statement at line number 8 concurrently, resulting in data races. There can be data races because of the control for dependence on the number of threads. As shown in listing 5, there will be data races only when the number of threads is more than 2. Here in our work, we propose a solution to detect data races statically. LLOV stands for LLVM OpenMP verifier, is language agnostic since we perform our analysis on the LLVM intermediate representation, which is language as well as machine independent. This helps us to handle OpenMP source code in Fortran as well as C and C++. We use a polyhedral dependence analysis of LLVM to compute the dependencies in the program. Since the polyhedral dependence analysis is precise in nature, we can conservatively state for some programs that they are data race free. The framework is also capable of generating task graphs for the OpenMP constructs. Figure 1 shows the overall workflow of our framework, where OpenMP source code in C and C++ is first compiled into LLVM IR. We use the Clang frontend for C and C++ source code and Flang frontend for Fortran source code. Since the LLVM IR is sequential in nature, we lose the OpenMP semantics in the IR. The first step is to reconstruct this OpenMP information from the LLVM IR. We then construct an in-memory representation of the OpenMP information, which is used by the OpenMP verifier. So this OpenMP verifier uses this in-memory representation to target the parallel constructs and model them in the polyhedral representation. Then we compute the dependencies present in the program using the polyhedral framework. Using these dependencies, we reason about the presence and absence of data races in the program. If a program is non-affine, that means it cannot be modeled in the polyhedral framework. We use the alias analysis, global motif analysis to detect data races in a conservative fashion. For an example, as shown here, we have multiple OpenMP directives. The in-memory representation for the example will look as shown in listing 7, where we will have a top-level parallel directive which will have list of variables and list of child directives. The in-memory representation can be captured by the BNF grammar, where we have a top-level directive which will have a directive type, an optional schedule, a list of variables, and a list of directives. The directive type can be one of the OpenMP supported directives such as parallel, for, SIMD, workshare, etc. Variables will have a variable type associated with it and a variable value. The variable type will be one of the data sharing attributes such as private plus private, shared plus private in reduction. So if we use this representation to separate out the parallel constructs into LLVM IR, then we construct a polyhedral representation of the parallel constructs. First, we ignore the parallel constructs and just compute the iteration domain, schedule, and access map of the sequential program. This can be represented in the polyhedral form as shown here. For the statement S0, we compute the iteration domain from the loop bounds. The access map maps the memory accesses performed by the statement S0 in a particular iteration. Here, the write operation to Bij is captured by the access relation from S0 ij to M of ij. Similarly, the read operation can be captured by the relation S of ij to M of ij minus 1. Using this information, we use the polyhedral framework to compute the dependencies present in the framework. These dependencies are valid only within the iteration domain of the program and any other constraints that are involved. Then we use this dependence information to determine if there are any violation of the data dependencies. Let us see pictorially how the algorithm works. Here for the example in listing 10, the dependence polyhedra is shown in figure 2. Every red arrow represents a dependence from one iteration to another. We can see that the dependencies are varying only in one dimension. This is a key insight in detecting parallelism in a program. If we take the projection of the dependencies onto a particular dimension, as shown in figure, where we have taken projection onto I dimension, the dependencies cease to exist. What we are left with are zero magnitude projections on the I dimension. This signifies that the particular dimension is parallel. Whereas if we take the projection onto J dimension, we are left with dependencies of unit magnitude, which represents that this particular dimension is not parallel. However, the user have marked the inner dimension as parallel as shown in listing 12. This will result into violation of the dependencies at runtime, which will result in data races. This is the key insight in detecting data races in our approach. We evaluated our work using 3 different benchmarks. We used data response C++ version 1.2. We use OMP SCR version 2.0, which is a commonly used data response in the literature. We have created a new data response in Fortran. We used 2 Intel Xeon processors with 72 number of threads and libOMP5 for our experimentation. We could compare our work against Halgrind, Valgrind DRD, Thyssen LLVM, Archer, and Sword. For the data response version 1.2, we have presented the maximum number of races reported across all the runs. Here TP represents true positive, FN represents false negative, TN represents true negative, and FP represents false positives. The best numbers are highlighted in red. Here, as we can see that Thyssen could detect maximum number of true positive cases, whereas LLV could detect maximum number of true negative cases. Since the coverage of all these tools are not uniform, we consolidated the common 61 kernels as shown in table 3. Here, all the tools could detect equal number of true positive cases, while Sword and LLV could capture similar number of true negative cases. In terms of performance metrics, LLV performs quite well in accuracy, F1 score, precision, and recall for data response version 1.2. Here the second base numbers are highlighted in bold. As we can see that LLV performs competitively against all the other tools. For the common 61 kernel, all the tools have equal recall. Here Sword performed well. LLV comes quite close second. However, the best part of LLV comes in terms of the runtime. Here in figure 5, we have plotted total execution time of the tools for different number of threads. The thread number varies on the horizontal axis and the execution time varies on in the vertical axis. The vertical axis is in logarithmic scale. We can see that LLOB performs best, which is highlighted by the dotted line. It takes just 44 seconds to analyze the data response version 1.2. Archer comes second, which is highlighted by the pink line, and Halgrind comes third, which is highlighted by the green line. For the common 61 kernels, LLV performs even better, which just took only 4.3 seconds to analyze the 61 kernels. Here Archer comes second, followed by Sword, which is highlighted by blue. For the OMP SCR version 2.0 benchmark, there are 14 kernels and many of the kernels have recursive programs. Since recursive programs are very difficult to analyze statically, LLV did not perform quite well in this benchmark. For OMP SCR also, the execution time of LLV is very less. As shown by the dotted line, LLV takes just 4.9 seconds to analyze the whole benchmark, whereas the other tools takes orders of magnitude more. Here Archer comes second, which is highlighted by the pink line, followed by Thyssen, which is highlighted by the orange line. Archer improves the time complexity of Thyssen, which is evident from this plot. We have created a new benchmark in Fortran to demonstrate that LLV can detect data races in Fortran code as well. So this benchmark is open source. Only 3 tools could detect data races in it. LLV could detect 36 true positive cases and 19 true negative cases. The coverage of LLV is less because the Fortran frontend flying is under active development and it did not support many of the OpenMP pragmas. This concludes our presentation. Here we have proposed a fast static data race checker for OpenMP programs. Also, it is freely available for download. The link is shown here. We have also open sourced the data response in Fortran. For any comments and suggestions and questions, please drop me an email at the email address shown. Any kind of suggestions and contributions in any form are most welcome. And thank you for your time.
Thank you very much, Uday. So we have time for questions. Please ask them on the Q&A if you can, or on the chat. So there is a question from Alex Inenko. So how difficult is it to recognize OpenMP constructs in LLVM-IR? As far as I know, most of them are just function calls to some glue or some glue instructions. do you think it could be possible to fix also some of these races automatically?
Yeah, this is a nice question. Actually, we thought about it, like fixing the issues automatically. Yeah, like the code generated by LLVM, a particular version of Clang is same, but however, once the version of Clang changes, there are minor changes in the LLVM IR. So we might need to deal with the minor variations, but we have definite plans to implement auto correction or auto bug fixing tools for OpenMP programs.
Okay, and how about the automatic recognition of OpenMP constructs at IR level?
Yeah, for that actually, we face some issues related to using Clang and Flang because both the front ends did not generate the similar, I mean, they are similar code, but they did not produce exact same code. So we had to tweak the analysis part to recognize the OpenMP programs. And I think there lies little problem in because of the different variations of the IR generated. Okay. I think there's like a framework that is under development to generate OpenMP code within LLVM instead of the front end. Maybe that will help in automatically detecting it.
Right, exactly. So I think that it's interesting to follow up on this. I mean, obviously, for research prototype, maybe you could deal with it as with pattern matching, but it's not very robust. So there are projects on the way. Yeah, don't hesitate to reach out.
Sure. Are
there more questions? I had a question as well. So very quickly, so can you say a bit about how the benchmarks fare in terms of like how dynamic they are? So how often you actually resort to alias analysis? How often you actually can compute precise dependence analysis? Do you have like statistics on this?
We did not have, I mean, specifically, we did not generate the statistics for the number of programs that the framework could not detect or analyze. But this is because whenever we could not analyze some segment of code in the Polyhedral framework, we used alias analysis to conservatively state the data races in it using the modref analysis.
And can you tell definitely how frequently you had to do it?
We did not have a statistics in it, but yeah, we definitely can add something like that. Yeah, thank you. Yeah.
Okay, thanks a lot for a very clear presentation. So we are going to switch on to the last presentation.
Thank you.
Last presentation will be IR to VEC, represented by Venkatakirti from IIT Hyderabad again. And this is joint work with a colleague from Indian Institute of Science, IISc. And please show the video.
Hello all, I am Venkat, PhD student from IIT Hyderabad, India. Today I am going to present our work, IR2VEC, a way of representing programs for machine learning applications. With the growth of open source hosting sites along with the community question and answer sites, the availability of open source codes along with its metadata is becoming more and more increasing and is led to something called as big code. While processing big data itself is challenging, processing big code for the purpose of automated tools for software engineering, for the purpose of compiler optimizations are equally challenging. If we take automated tools, we have several interesting applications like summary detection, similarity detection, code summarization, or code suggestion. They are hard because of their nature of being undecidable, as well as if we take compiler optimization applications, we have applications like inlining, unrolling, or prediction of vector factor, phase ordering. These are all equally hard because most of these are NP hard or NP complete in nature and are often driven by heuristics in modern compiler. So how do we solve the problem? It has been shown that machine learning approaches have been performing better. So if we take NLP tasks, we have vertex or glove-like approaches to represent the underlying text, or if we take images, we have sophisticated infrastructure like CNN or AlexNet to extract the feature so that can be useful for representing the underlying information for downstream tasks. So if we take programs, how do we represent them? This forms the basis of the problem statement. And to this end, we propose Iterative, which is based on LLVM IR to represent programs in distributed embeddings where the semantic meaning of the program is distributed across the components of a vector. And we use an agglomerative or a bottom-up approach to represent programs that makes the approach simpler and makes it amenable with simpler machine learning models. So how do we form representations? First, we generate vocabulary called a seed embedding vocabulary by taking the source program and generating the corresponding LLVM IR. This LLVM IR is decomposed into triplets by using three important relations. First is a type of relation that relates the opcode of the instruction with the type of its instruction. And second is the next instruction relation that relates the opcode of the current instruction with that of the next instruction. And third is the argument relation that relates the opcode with its arguments. Such triplets are labeled as H, R, and T, denoting head, relationship, and tail. And we use a machine learning model called Transy to learn a relation H plus R minus T is equal to 0 by minimizing H plus R minus T. And this training process results in a seed embedding vocabulary where each of the entities of H, R, and T get an n-dimensional vector representation. And we store them, and this vocabulary is called seed embedding vocabulary. So after learning the seed embedding vocabulary, we use the learned values to represent program. For this, any LLVMIR is decomposed into entities, and this learned embedding vocabulary is looked up and to fetch the corresponding representations. And these representations are composed together to form instruction vector. This vector is annotated with the flow information of the program, like useDef for reaching definitions. And we collect all the live instructions to form basic block vector. This in turn is used to form function vector, a program vector. And these representations can be used by several machine learning models for different downstream tasks. So as mentioned, the instruction vector is a composition of entities of the instruction. It is obtained by linear combination of opcode, type, and arguments. We choose a heuristic that the weight of the opcode is greater than that of the type, which in turn is greater than that of the arguments, in order to maintain uniformity. And now what we do is we annotate flow information by making use of the representation of the definition in place of the use, like what we have shown here. And then such representations are used to form vectors at the basic block level. In case of interbasic block representation, as more than one definition can potentially reach its use, we conservatively make use of all the representations in place of the use of the particular variable or a pointer, and then we form the instruction vectors. And such way of learning representation results in more meaningful clusters. As we can see, all the integer based operations are grouped put together and floating point operations are grouped put together. So is the case of arguments as well as for the pointer based operations. If we have a look at the casting operations, all the integer based casting operations, or those that operate on integers, are put together along with the integer based operations, and those that operate on floats are put together with the floating point operations. If we have a look at the types, vector type is positioned equidistantly from all other basic types, showing the semantic equivalence. We perform two case studies using the learned representation, and the first is heterogeneous device mapping. Here the problem is to map OpenCL kernels to optimal target, a CPU or a GPU on a heterogeneous architecture. We all know that GPU is always not the best choice, so is the case of CPU. So it depending on the kernel and the GPU architecture, we have to make an optimal right choice. So for this, we make use of gradient boosting classifier using the learned representation on two different platforms, AMD Tahiti and NVIDIA GTX, replicating the available dataset. As we can see, the accuracy obtained by Iterative embeddings are higher than the baselines, and so is the case of speedup, where we perform better than all the baselines. If we take closer look at the results, kernels like embarrassingly parallel that gives optimal performance when run on GPU are mapped correctly in all 10 turns of the cross-validation, and kernels like LU that gives an optimal performance when run on CPU are mapped correctly with a high confidence of about 95%, and all these predictions often lead to lesser slowdowns when compared to the other works. And even with respect to training time, we perform better. We just take 5 seconds on a P100 GPU when compared to the other works. This leads to a slow reduction of about 7,000 to 8,000 times reduction in the training time. And moving on, the next case study is prediction of thread coarsening factor. Thread coarsening is process of fusing two or more concurrent threads, and coarsening factor is number of threads that can be fused. Optimal thread coarsening factor often varies across architecture and across kernels. So a thread coarsening factor for a kernel that gives a best performance can lead to very poor performance in another architecture. We performed this experiment on 4 different devices following the available dataset. And even in this experiment, the predictions by Iterative result in better speed up when compared to the baselines, as you can see here. And in case of NVIDIA's GTX and Tesla's, Iterative predictions are the only ones that obtain positive speed up when compared to the other methods. And if we have a closer look, the kernels like SPMV and MV Kaul that respond poorly to coarsening, the Iterative predictions obtain baseline speed up without causing slowdowns, and these predictions obtain best speed ups in about 70% of the cases, and it also rarely leads to slowdowns. It is obtained only in 8 out of 68 cases, and even in these cases it is within 10% of the baseline. Even in this experiment, training time is very less. It just takes 10 seconds on a P100 GPU. This results in a reduction of about 360 to 4,000 times in training time when compared to the recent works. When compared to the earlier works that use AST path level representations or instruction level representations, Iterative did not encounter any out of vocabulary issue, as the initial vocabulary representations are based on the entities, and these entities are in turn composed to form the representations at the level of program. And to conclude, we proposed Iterative, a way of representing programs using flow information for machine learning applications. Such a representation is independent of the source language as well as the underlying application. And this is a non-data hungry method which maintains a small vocabulary. And this method did not encounter any out of vocabulary issues, as we followed a bottom-up approach for forming representations. Because of the suitability for lightweight, simpler machine learning models, most experiments take a lesser training time. And thank you very much for listening to our talk.
Thank you very much, Utpal. So there are a couple of questions on the Q&A both by Alex. First one is, have you observed any issues related to the size of the LLVM IR instructions? So basically how large they expand into like low-level assembly code, for example. So is this something you can actually capture? Does it have, is there a way to represent this?
Right. So this is a nice question, actually. So what we do is we capture and form the representations pretty much early in the pipeline. As I was explaining, we decompose them and form representations separately. Say GEP, opcode of GEP will always have a particular n-dimensional vector, as well as all these arguments individually have some similar n-dimensional vectors. And then it's all about composing them for a particular application. So in effect, so we don't observe any issues while forming representations for any arbitrary length.
I'm sorry, I said Utpal, obviously it's Sanket. Second question, it's a follow-up. Do you think we need another IR, or that's friendlier to ML embedding, to representation learning than LLVM?
So objective of the work is that we wanted to make use of LLVM IR to make it ML friendly. So that was the objective, but yeah, so there is potential for having a modified version of, say, even MLIR based representations that can help us in getting better representations, etc. Yeah.
Okay, right. So there's something in the chat that is related with the previous one. So I have a question as well. So it was not very clear how much, how different it is, or actually what methodology for training do you use? So do you actually retrain for every use case? Do you retrain the representation for every use case, or do you have a common one that you apply?
Not really. So the initial vocabulary is trained just once. And it is independent of downstream tasks. So it is, you can consider it as an unsupervised way of learning representations. And then once this vocabulary is formed, then the training process is specialized for the application.
Okay,
so the representation in turn
only the vocabulary is shared, is trained once.
Correct.
Okay. Are there any more questions? Don't think so. So we are a little bit late. So we should thank Venkat again. So thank you all for attending this first session of the TACO papers of Heinecke. So we are a little bit delayed due to technical issues at the beginning. Apparently I was the culprit because I selected the wrong link. But it seems to be working pretty well. So I hope we have strong attendance and Q&A in the following sessions as well. So we have time for a break. There are booths like industry sponsors willing to interact with you. And so see you in 20 minutes.